Right now, at this very moment while you're watching this video, there's a tiny spacecraft racing alone through space over 24 billion kilometers away from Earth. And here's the craziest part. This spacecraft was launched 47 years ago, back in 1977, when there were no smartphones, no internet, no GPS, none of the technology we use every single day. And yet this machine is still alive today, still sending signals back to Earth, which honestly is nothing short of a miracle. Its name is Voyager, and it's the farthest-reaching thing humans have ever built. Now, Voyager's story is so long, so deep, and so mind-blowing that I decided not to cover it in just one video. Instead, I'm breaking it into a 3-part series so you can really soak in every single detail. This is part 1, where we'll find out how this mission actually began, what once in 175 years opportunity made it all possible, and what Voyager saw at Jupiter that left scientists around the world completely stunned. So our story begins back in the 1960s. At that time, NASA had a brilliant engineer working for them named Gary Flandro. Now Gary was the kind of guy who absolutely loved studying the motion of planets. This man spent day and night running calculations, figuring out which planet would be where, how fast it was moving, and what position it would be in years down the line. And one day, while running these calculations, Gary stumbled onto something that literally changed the entire direction of space science. He discovered that around 1977, the 4 biggest planets in our solar system, Jupiter, Saturn, Uranus, and Neptune, were about to align in an incredibly rare position. Now, you might be wondering, what's the big deal about an alignment? Well, listen closely, because this is the most interesting part. See, normally, if you wanted to send a spacecraft to visit all 4 of these planets one by one, you'd need a separate mission for each one, costing decades of time and billions of dollars. But in 1977, these 4 planets were lining up in such a way that a single spacecraft could be launched and fly past all 4 planets one after another. Think of it like this. Imagine you have 4 friends you need to visit, and normally they all live in totally different directions, so you'd need 4 separate trips. But suddenly, one day, you find out that next week, all 4 of them are going to be lined up on the exact same road, so you can visit all of them in a single trip. That's exactly what was happening with the planets. And here's the mind-blowing part. This alignment only happens once every 175 years. That means if they didn't seize this opportunity in 1977, the next chance wouldn't come until the year 2152. In other words, neither we nor Gary would ever live to see this opportunity again. So when Gary brought this discovery to NASA, everyone realized this was a once-in-a-lifetime opportunity, one they simply couldn't afford to miss. But there was a massive problem. These planets are so far away that if you tried to send a spacecraft there using rocket fuel alone, there simply wasn't enough fuel on Earth to make the journey possible. Jupiter alone is 620 million kilometers from Earth, and Neptune is a staggering 4.5 billion kilometers away. Covering that kind of distance on fuel alone was practically impossible. So what was the solution? The solution came from a brilliant piece of scientific trickery called the gravity assist, or the slingshot effect, and it's actually pretty simple to understand. See, every planet has gravity, a pulling force that draws things toward it. The bigger the planet, the stronger its gravity. Now, when a spacecraft flies close to a massive planet, that planet's gravity pulls the spacecraft toward it. But if the spacecraft approaches at exactly the right angle and speed, it doesn't get trapped by that gravity. Instead, it curves around the planet, steals a burst of energy from its gravity, and shoots off even faster than before without burning a single drop of extra fuel. Here's a simple way to picture it. Think of a fast bowler in cricket hurling a ball at 150 kilometers per hour, and the batsman uses that same momentum, adds the force of his bat, and sends that ball flying over the boundary at 200 kilometers per hour. The ball's own speed plus the bat's force combine to make it go even faster. That's exactly how a gravity assist works. A planet's gravity gives the spacecraft an extra speed boost. And Voyager used this trick not once, but multiple times. First, it grabbed speed from Jupiter's gravity, then from Saturn's. And by doing this over and over, it built up so much velocity that even the Sun's gravity couldn't pull it back. It was basically a way to get free speed, and that's exactly what made the entire mission possible. NASA then decided to build not one but two spacecraft, so if one failed, the other could still carry out the mission. These two were named Voyager 1 and Voyager 2. And here's a fun twist. Voyager 2 was actually launched first, on August 20th, 1977, while Voyager 1 launched later on September 5th, 1977. Now you might be thinking, if Voyager 2 launched first, why wasn't it named Voyager 1? Well, the reason is pretty simple. Voyager 1 was put on a shorter, faster trajectory, so even though it launched later, it ended up reaching Jupiter first, and that's how it earned the title of Voyager 1. Both spacecraft also had different missions. Voyager 1 was only meant to study Jupiter and Saturn in detail before heading straight out of the solar system. Voyager 2, on the other hand, was tasked with visiting all four planets, Jupiter, Saturn, Uranus, and Neptune, which meant its journey was longer and riskier. Now, when it comes to the actual build of these spacecraft, here's something that'll surprise you. Voyager is about the size of a small car, weighing just 825 kilograms. The idea that something this small managed to travel this unimaginably far is mind-bending all on its own. The engineers who built it faced a ton of major challenges, but the biggest one was power. See, there's no electrical outlet floating around in space, what you can't just plug in and charge up. So where would Voyager get its power from? The first option was solar panels, but those simply wouldn't work out here. Why? Because the farther you travel from the sun, the weaker sunlight gets. By the time you reach Jupiter, sunlight is 25 times weaker than it is on Earth, and by Saturn, it's a whopping 90 times weaker. In light that dim, solar panels become basically useless, so NASA turned to a completely different technology called an RTG, a radioisotope thermoelectric generator. Don't let the name scare you off, it's actually pretty easy to understand. Basically, inside it, there's a radioactive material called plutonium-238. Now, what does radioactive material do? It slowly breaks down on its own, and in that process, it generates heat. Kind of like when you rub your hands together really fast on a cold winter day and they warm up. In the same way, the atoms inside the plutonium keep breaking down and continuously releasing heat. The RTG then converts that heat into electricity, and this process keeps running for years without stopping. The only catch is that over time, the plutonium depletes and the power output keeps dropping. When Voyager launched, it was putting out 470 watts of power, enough to run about 4 or 5 light bulbs. And today, in 2026, that number has dropped to just around 250 watts. So what are NASA's engineers doing about it? One by one, they're shutting down Voyager's instruments so that whatever power is left can keep the communication systems running, so Voyager can keep sending us data. Scientists estimate that somewhere between 2028 and 2030, Voyager will send its very last signal, and after that it will go silent forever. Now, there was another huge challenge: communication. How exactly does Voyager send a signal back to us from that unbelievable distance? Voyager carries a massive 3.7-meter wide dish antenna that transmits signals using radio waves. And here's the crazy part. The power of these signals is just 23 watts. That's less power than the tiny light bulb inside your refrigerator. And yet, this incredibly weak signal travels billions of kilometers and still reaches Earth. To catch these signals, NASA has set up massive 70-meter wide antenna dishes at 3 different locations on Earth known as the Deep Space Network. These dishes are so sensitive that they can pick up even the faintest whisper of a signal. And here's the craziest part of all: Voyager is now so far away that even though its signal travels at the speed of light, it still takes over 22 hours to reach Earth. That means if Voyager sent a message right now, we wouldn't get it until tomorrow. And if we replied, Voyager wouldn't receive it until the day after. A simple back-and-forth conversation takes a full 2 days. Now, along with the spacecraft, there was one more incredible thing attached to it. Something that makes Voyager way more than just a machine. Both Voyager spacecraft carry a golden record. This is a 12-inch gold-plated copper disc that stores information about Earth and humanity. It contains 150 photographs, greetings in 55 languages, and sounds of nature like wind, rain, thunder, ocean waves, and birds chirping. It also includes music from different cultures, and the smartest part of all is that the cover of this disc has diagrams engraved on it explaining exactly how to play it. The whole idea is that if someday some other civilization out there in the universe happens to find this spacecraft, they'd be able to figure out where it came from and who sent it. It's a wildly far-reaching idea, but just think about how big the vision was. Those scientists created a message that might not be found for millions of years. We'll dive deeper into the golden record in part 2. Now we get to the most exciting part of this whole story, Voyager's journey and its discoveries. Voyager 1 reached Jupiter in March of 1979. Jupiter is the largest planet in our solar system, and just how big is it? Well, if Jupiter were hollow, you could fit 1,300 Earths inside it. 1,300. That means Earth compared to Jupiter is like a tiny marble next to a soccer ball. Now, Jupiter had already been observed through telescopes before.